Okay, so today's a transitional week on this course, in that we're going to finish the theory of type theory. When I say finish the theory of type theory, there's a lot of theory of type theory we haven't done, but we're going to finish the theory of type theory insofar as we're going to cover it. And then from next week onwards, so this week the exercise classes will cover what's been covered in the lecture again, like they've been doing the previous few weeks. But from next week, the lectures and exercise classes are going to diverge, and in the lectures we're going to go off into lots of other aspects of logic in computer science, whereas in the exercise classes, from which you will have a break next week, because Luna's not here next week, but starting from 2 weeks from now, you'll be pursuing a project in the exercise classes in type theory, so building on the foundations that we've built for type theory, and that project will contribute 40% of your course mark. You may remember from the first lecture, I said that there will also be a student presentation as part of this course, which will contribute 20% to your course mark. And those student presentations are going to take place in the last hour of the lectures in the next period of lectures covering all the other topics of logic and computer science. So the second thing I want to do today is to discuss student presentations and the logistics for it, how to organise yourselves, and what sort of support I'll provide. So that's the second part. And the second part is not going to be examinable material, of course, because it's about the logistics of presentations. I would like it to be informal and chatty, and I don't particularly want it to be recorded and put on the web. So I'm just going to, with the video, I'm just going to put the theory part in the video, and the second part we're just going to discuss between us. The other thing is, I think even taken together, there's not really 3 full lecture hours, meaning 3 full 45 minutes of material here. So I will, assuming I feel that we're up to speed at the end of the first hour, we probably will have full breaks, but still aim to finish at 11:45. Okay. Any questions on that? Right. Okay. So we want to continue with type theory. So I'm going to start, I think, like in the exercise class last week, and remind ourselves where we are in type theory. And a nice way of doing that is to, in the type theory, we've got these rules, and in the rules we derive things like the main rule we have establishes what we call judgments of this form. So we prove that some piece of syntax, which we call a term, belongs to some other piece of syntax, which we call a type. And the types are intuitively are collections of things, like data types are. And the piece of syntax, when we establish this, we show that this is a legitimate piece of syntax for describing something of the form that this type is, the set of things that are in this type, so to speak. But because the types are themselves quite complicated, they're dependent types, so they might contain variables and terms in the types themselves, and we build them up using rules. It's not that there's just some very simple grammar that describes what the types are. Because of that, we need to actually prove that piece of syntax A is a type. We need to do that prior to forming any judgment of this form. So, but in order to prove this, we will have needed to, along the way, prove that A is itself a type. So that gives us another judgment form, which we're writing like this. A is a type, which is not quite the same thing because type is not itself a type. So this, and in fact, if you added a rule saying type is a type, then it's a famous result that type theory becomes inconsistent. It's a little bit related to Russell's paradox. Actually, it's more closely related to what's called the Borelli-Forti paradox. And it doesn't really matter. Type cannot itself be a type. Get into problems if you say type is a type. So this, we need to have proved A. And in the way I've presented type theory, these are all our basic judgments, only these. So maybe you did this in the exercise class, but maybe not. So let's just consider the other judgments that we think we have, and we'll see that they're all instances of these two judgments. So one important thing, we were dealing with logic and type theory, so we had this, so this is called the universe of types, but we had another universe, a propositional universe of propositions called prop. And we didn't just want to establish, we wanted to use prop for expressing properties, so we wanted to establish syntax for logic and establish that the logical formulas are indeed propositions. So we had for that another judgment form phi prop. And phi is a proposition. But this is a derived judgment form because prop, at least in our formulation, prop is a type. So prop is something that we can have an A for, and then phi is just a term of type prop. Okay. So this is an instance. Oops, let's put that in blue. Instance of T in A. And then we had another very important judgment, just phi itself. And this was the judgment that said that in order to do logic, we wanted to prove that things are true, so to speak, under our assumptions, or provable would be a more constructive way of looking at it. Because in constructive logic, we tend to emphasize provability over truth, as I discussed last week. So we just had the judgment phi itself. But really what that's a shorthand for, when we prove phi, we actually, what we're doing is we're showing that some term inhabits phi. So there is some term, not some term in phi. Every proof of phi gives us a term that inhabits phi. So really, when we were writing just phi on its own, we could say it means somehow this, where here I use this underscore notation like people sometimes do as a sort of wild card, if you like. So what I mean here is we establish, in order to prove phi, what we're really doing is we're proving that some term inhabits phi, the type phi, we should read that term as this term is a witness for the proposition phi, or witness or proof, And I'm writing an underscore because we're not actually really always very interested in that term. But still, the point is it fits into just these two basic judgment forms of type theory. So all we need are these two judgment forms so far. So these are derived judgment forms at the start. Oh, now judgment with an E here and without an E here. In my notes, I don't have an E. There's some difference between American and UK spelling, but I don't remember really which is which in this case. And I think in like the type theory literature, one tends to use this one, but I'm not sure. Anyway, never mind. Who cares how we spell it? So today we're going to meet later on another judgment, which is going to be a judgment. Oops. So today we will introduce later. Let's see how I'm writing it. We're going to introduce another judgment, which is actually crucial. It's a bit subtle, but it's crucial for the formulation of type theory. I presented lots of rules. There's a really important rule that I've missed so far in my presentation. And it relies on this judgment form, which we'll talk about later. So today we're going to introduce this one, and this says S and T are terms of type A that are judgmentally equal. So again, question whether to put the E in here or not, but that's not so judgmentally equal. I won't say intuitively what that is at the moment, but we'll come to it when we get there. So this is so today we'll introduce this. It's a really fundamental. You can't actually the type theory we've presented so far is essentially incomplete. You've been able to work with it because somehow one can work with it informally without worrying too much about this rule. But in order to have a precise type theory, it's implemented in proof checkers. This judgment form is really critical, and the rule related to it is really important. Okay, so we're going to get to this in due course, but in order to get there, I want to go back. Yes.
There you said that by the problem instance of P is a type A, if the proposition themselves are types, would that be an instance of A is a type?
Aha.
The first one.
Very good. So propositions are also themselves types. So that's an excellent point. It is indeed an instance of both. This every proposition is a type and because everything is a proposition is, well, sorry, it's not really an instance of this, because here we're saying phi is a prop. It will follow that phi is a type, but when we say phi is a prop, we're saying something stronger. Okay, but it's a very good point. So it's not such an instance of this. In this case, it follows from this that phi is also a type. Okay. Good. Right. So one goal today is to get to this to get to this judgmental equality. But before doing that, I want to go back to the types we were looking at last week, the natural numbers lists, and vectors. And last week we had the introduction rules for these types, so how to form terms that describe elements of the types. But as I've been emphasizing throughout the treatment of type theory, every type form that we have has several kinds of rules. So we have the formation rules, which we have for natural numbers, lists, and vectors. We have the introduction rules, which we saw last week for natural numbers, lists, and vectors. And we also have elimination rules and computation rules. And those rules we haven't seen for natural numbers, lists, and vectors. So let's look at those rules now. So remember, for the natural numbers type, we originally wrote it down in this form. We have the introduction rules of giving us rules that tell us what the basic syntax for natural numbers are. And they were very crude, and that all we had was the rule that tells us that 0 is a natural number, and the rule that tells us that if we derive the sum term n, it describes a natural number. So this can be any term here. Then any term that we prove describes a natural number. Then you can form the successor term, which describes intuitively the successor natural number. What the elimination rule tells us is, so here we've got ways of building natural numbers, terms of the form natural number. But for the elimination rule, if we were going to write it in the standard format, then we assume that we've proved some term is a natural number, and the elimination rule is how we can use that information. So just like the elimination rule, if we've got the sum type here, we have T is now the sum type. Well, to use that information, we needed to say what we can do with T if it's in the left half of the sum type. So we had one premise, what we can do with it if it's in the left half, and what we can do with it if it's in the right half. And the natural numbers are intuitively like an infinite sum of things. So an infinite, we're taking one element set and co-producting it with itself or plussing it with itself infinitely often. But obviously we can't have an infinite rule because that wouldn't really help for reasoning. The question is, what can we infer if we've got some term T of type nat? What can we prove in general? And the basic principle that allows us to eliminate here is the principle of mathematical induction. So if we have a property, so what I'm going to start with is not the final rule for the natural numbers. And in fact, I'm going to start in one form and then go into another form, which is more convenient in a sense. So we're going to evolve there. And the notes that are online just present the final story. But in the lecture, I want to tell you sort of intuitively how we get there. So what we're going to prove here, the idea is that if we've got a term T that's a natural number, then as a first approach to an elimination rule, we might say, well, in that case, what we can do is, if we can apply induction and show if we've got some property P that holds for 0. So suppose we've proved that P holds for 0. So here P, thinking of P as a predicate on natural numbers. So that means we're assuming that, let's even put that as a premise in the rule. So we assume that we've got some predicate on natural numbers. We've proved that P holds for 0.
One question is that P holds for 0. It would be the same that if we had, like, for example, a box, and on the top we have 0 from natural numbers, 3 dots P0. So from zero that is a natural number, we can conclude P0.
So when we have an assumption, so when we're deriving things, we're always deriving judgments that a term is in a type. And when we make an assumption, the only assumptions we're allowed to make are some variable belongs to a type, where this is some fresh variable that we're not talking about somewhere else in the proof. So we can assume we've got some x of type natural numbers, but zero itself, we don't need to assume it's a natural number because we can prove it's a natural number. Okay, so if we've got some syntax P for a predicate, given a natural number gives us a proposition, this is like a function from natural numbers to propositions, so we can certainly apply it to zero, and it's a proposition. So then it makes sense to look at the judgment that says P of zero is true. So this premise is saying P of zero is true, which now in type theory we know is we've proved some term of type P0, but I'm going to continue with the same notation I was using before, that this is, I want to make it look like a logical rule. So here we've established T is some syntax for a natural number. It might contain some variables, it might contain some complicated functions, something that will compute to a natural number. We've got some complicated syntax for some property of natural numbers. We've proved P of zero, and we're going to just do the usual mathematical induction. So now we use an assumption, because the usual induction step is assume P holds for x and prove it for x plus 1. So if on the assumption that P holds for x, but if on the assumption that x is a natural number and P holds, so we need to make two assumptions here because we assume we have a natural number x such that P holds for x. If from those assumptions we can derive P holds for the successor of x, then under those conditions P holds for T. P holds for, we could conclude for all natural numbers P holds for the natural number, but then it doesn't look so much like an elimination rule. Here we've eliminated we've got, the elimination rule. The idea is we've established we've got some element of the type nat, what can we do with it? And this is what we can do with an element of the type natural numbers. It's one thing we can do, and it's like the induction rule. This is a first, so here again, this is from these assumptions, we've established this. It goes in the box. Okay, so we've got an induction rule. So this is as a first attempt, the elimination. So we're going to do something like this, but something more general and more powerful. And actually, at this stage, we've got enough machinery and type theory that it gets actually a bit cumbersome writing things in this rule form with all these boxes and so on, when we can just write things in straightforward logic, in more straightforward, I was going to say logical terms, but ultimately it's really type theoretic terms. But we'll start with logical terms. So let's think about this induction rule. Or maybe even before that. Let's do it. So we want to go to a more straightforward, in a sense, formulation. Rather than using rules, it turns out to be somehow more straightforward to just give the rules in terms of defining constants that have types that implement the rules. So rather than, instead of a rule-based formulation, as on the other board, we assume constants of specific types. We assume constants, or let's say typed constants, that implement the rules that are equivalent, essentially. I'll put it in quotes because it's a little bit subtle how they're equivalent to the rules. So the first two we already did last week. This rule is in any case just saying we have a typed constant. We have the constant 0, which is a natural number. So the intro rules become, instead of rules, they're typed constants. So we have 0, which is a natural number. And we have successor, well, we can apply it to any natural number. So it's a function from natural numbers to natural numbers. We just give ourselves a basic constant, suc, a successor of type natural number, arrows natural number. Now, it's not strictly speaking directly equivalent to having this rule, because if we have this rule, we cannot prove using this rule, we cannot prove the judgment suc. So if we have suc as a constant of this type, then that gives us an immediate proof. The idea is it's added as an axiom, so we can certainly derive suc is a function of natural numbers to natural numbers. If we have this rule, we can't derive that suc is a function from natural numbers. We can't derive that. But what we can get is that lambda x in nat suc x is a function from natural numbers to natural numbers. Okay, so there's that little minor difference, but we do still have a function from natural numbers to natural numbers that has the effect of acting as a successor. It just, the syntax, we can't literally ever prove that in this formulation with rules. That's the only real difference. But still, conceptually, it's the same thing. And it's quite simple to say, okay, we have some basic constants, a 0 constant, and a successor constant. In the same way, rather than having this rule with boxes and things like this for induction, for the elimination, we can say, well, let's just formulate induction as an axiom in logic. And, think pretty much we've all seen this sort of thing before. So induction is simply stated as an axiom. So if the axiom would be P holds for 0, and I'm going to put that as an implication because I'm going to say if P holds for 0, it implies that if for all n P holds for n implies P holds for n plus 1, then P holds for all natural numbers. So let me just write it rather than it's complicated to say nested implications with universal quantifications, and it's complicated to speak the principles, but so let me just write it out and then we'll look at it. Okay. So hopefully this looks familiar to everyone. If P holds for 0, and for all natural numbers, if P holds for x, P holds for the successor of x, then for all natural numbers, P holds for x. It's kind of how you would write induction as an axiom.
Excuse me, I have a question. So here, okay, I wanted to ask whether you're using spot encoding, but it's actually the same in this specific instance.
Right. Well, it's a good question because we're about to get to that. And you're right. And your conclusion is also, your answer to your own question is also correct. For those who didn't follow that, it doesn't matter because that's one of the things we're about to look at. So one question here is, what is P? So here we establish, as premise in the rule, we said P needs to be a predicate on natural numbers. Otherwise, the whole thing doesn't make sense. So actually, we can, because we've got a nice logic where we can quantify over arbitrary types, we're going to actually start this with, because this principle applies to, I don't even have enough space there, but this principle applies to all properties P, all predicates P on the natural numbers. Okay. So that goes around the whole thing. All right. So this is the statement of induction. And we might just say, so I'm going to, this is still only an approximation to what we get, but we're getting closer. But we might just say we have something constant, let's call it, let's use a capital letter for it because it does. So we have a constant which we'll call ind, which is the assumed proof, which is our elimination. And like the proof is like the name for our elimination rule for natural numbers, which is of this type. Okay. Now it doesn't look very type theoretic at the moment because we have these universal quantifiers in. Well, I mean, we'll be using those, but remember, the universal quantifier is the same thing last week as the dependent product type. So we can replace all the universal quantifiers with pi's. But there's another thing we can do. So this is okay, what we've got here. But there's another thing we can do, which we're going to do in a moment. Another way of generalizing it. So I'm going to rub off what's on this board and remind you of, or maybe remind you, or otherwise inform you of some context, which is not massively important if it's too out on a limb for you, so if it's too off to the side. But normally in mathematics, if we define mathematics in set theory, induction is a basic principle of the natural numbers. So in mathematics, induction, which is basically this, but P0 of all x the natural numbers here that is given 1 implies for all x here that is a basic principle. And in the set theoretic universe of maths, we use this to derive something called the recursion theorem. And which I'll tell you what it is, but and then a mathematical proof in set theory derives from this. The recursion principle, what's called the recursion principle. So here, I'm just talking about set theoretic mathematics. And the recursion principle says if we have any set A and an element A in A and a function from A to itself, an element little a of A and a function from A to itself, then there exists a unique function R, the natural numbers to A, such that R of 0 is little a, and R of any number n plus 1 is f of R of n. And what this is saying is, whenever we have a set with an element in it, a distinguished element, and a function on the set, then there's a unique sequence of elements in the set where the 0 element is the starting element, the delay, and the other numbers are just iterates of the function f on that starting element. So for any element and function in and on the set, there's a unique function for the natural numbers that iterates the function, the natural number, many times, starting with the starting element. Okay, so the usual principle in mathematics is to go, we have induction as a basic principle, and then with a complicated set theoretic proof that requires a lot of the power of set theory, one derives this recursion principle from it. It was a beautiful observation of Martin Love's when he was constructing the type theory, but from a type theoretic perspective, recursion is just a natural type theoretic generalization of induction. And what that means, so this is our first attempt, but we're going to do something more general. So the induction as we formulated it works for predicates on the natural numbers. That's how inductions normally formulated. It's a map from map to prop. Every proposition is a type, is itself a type. So this is a special case of a map from natural numbers to types. And so it's natural to replace this with the same thing, but we replace prop with types. So then arrow becomes function space, which is the same as implication under the interpretation of logic in type theory under both interpretations of logic in type theory that we did last week. And the universal quantifier becomes dependent product type, which is again the same thing. You know, the universal quantifier is a special case of the dependent product type in both interpretations of type theory, namely the type, the case in which you've got a proposition here rather than a general type. So we replace what's in green with the final principle, which we call the recursion principle. So we say we've got a R. So we're going to give our constant a name, which I think in my notes I just called it R. Okay, R doesn't that because it's the recursor, the natural numbers type. And what it says is, instead of for all, we say for all. And do I still say P? Yeah. So we ask instead of, instead of asking for a predicate, we say we have a family of types indexed by natural numbers. It's actually more powerful than this recursion principle because it's saying we've got actually a family of sets A indexed by n and the f sub the f's act accordingly. It doesn't really matter. I'm just going to simply from a formal point of view, we simply replace all the rules with pies and we replace prop with type. So Gregor, you have
yes, I didn't need to interrupt it right now.
This is we just. So. That seems to be the same as what I've got in the notes. Except I call the variable n in the notes because it's a numbers variable. Doesn't really matter. So put this in the red box because this is. So this replaces this because this is a special case of this. Okay, whenever we have a P from map to prop, that is in particular a P from map to type because prop, every proposition is a type. And the rules are literally just, the interpretation of the rule in type theory is literally just type. Okay, so Gregor,
So I suspect that we can't prove that next to type is a type, and we need this to be a type in order for line of formation. Because
that's a very good point. Yeah,
we need like the type in type one.
That's true. So this doesn't actually fit in with the rules. That's an excellent point that I missed. So map to type. So I think we take it as a meta rule that let's ignore that problem. That's an excellent point. Yes, very good. And any other less good questions that I can answer more easily with a better answer?
That was, you also said that like we can't prove that SAC is of type next to net.
Yeah.
But if we can have either equivalence as you wrote down, and that would just consolidation.
Well, if you had eta equivalence normally assumes you have typed terms on both sides. So if you formulate it in a type theoretic way, so you still wouldn't get it because to show syntax has a type doesn't go through equality rules, it just goes through typing rules. I mean, it goes through judgmental equality rules, as we'll find out later. Okay, well, it's break time, so 2 minutes to 9. So we're going to have a full break. So we start again at 13 minutes past by the clock on the back wall. Okay. So we now have the introduction rules, the elimination rules, and the next thing to do will be the computation rules. And in order to do the computation rules, I need to explain a little bit how to understand this elimination rule. But before doing that, I'd like to go back to the point Gregor raised in the last hour, which was a very good point. So it's not fundamental for you to understand it, but for those who do understand these comments, I'm making your benefit. So the issue is that we were only allowed to form the function space type between types. And type is not, as I said at the beginning today, type is not itself a type. So even this is misformed according to the rules I have given. And then the type associated with the variable quantifying over also itself needs to be a type, and I've also said this is not a type. So the way this is resolved in the usual proof assistance and in a more formal version of type theory that I've been talking about is to say, well, we stratify the notions of types into what are called type universes. And here we need to say which type universe we're going into. So the smallest one might be type sub 0. And then we would have another universe of type sub 1, which is larger, and it would allow type sub 0 would itself be an element of the universe type sub 1. So type sub 0, the collection of all types, of all small types, is not itself a type, but is not itself a small type, but you could consider it a larger type in a larger, then you could consider it a type in a larger universe of types, which would be type sub 1. then type sub 1 would be an element of type sub 2. So you have this hierarchy of universes, and you will probably meet these in the proof assistance that you'll be dealing with in the exercise classes. So I'll leave that consideration, that worry to you'll get the correct way of dealing with these size issues in the exercise classes, so to speak. For the moment, we won't worry about it. We'll just assume we're allowed to call this as some sort of special type that we're allowed to use in this formation rule. There are other ways around it, but I don't want to spend too much time on this. It is an excellent point, and next time I teach the course, I will reconsider how to present things because of this. So this doesn't actually fit in with the rules that I've given. Anyway, let's consider what it means. This is called the recursor. It's the eliminator for the natural numbers type. It's called a recursor. And in order to understand it in a little more detail, let's consider how we might use it. So it's a constant of this type. So if we want to use it, well, it's an element of a dependent product, which is like a function, which expects P, which is a type family. So a natural numbers index type family, or a function from that to type as an argument. So we're kind of interested in looking at R sub nat applied to such a P, where P is family of types indexed by natural numbers. And once we've given it that argument, it's now a nested function space. This is the first argument, this is the second argument. So the first argument will be some element, little b, of type P of 0. So P of 0 is a type because we've applied P to 0. And the second argument has this more complicated type. It's a dependent product type. So it's a function from natural numbers to a type that's dependent on the natural number to a function from whatever P of x is to whatever P of successor of x is. So we need the second argument is some f from, I call it f, yeah, from which is P x in that, P of x to P of f of x, oh sorry, suc of x, successor of x. And what this gives us, when we've given it these three arguments, well, it's still a function that takes natural numbers to P of x, but I'm not going to give this argument, I'm just going to consider it as a function or a family of elements. For every natural number, it's a function from natural numbers to, for each natural number n, we get an element of the type P of n, whatever that is. And I want to present it like this because the computation rules are going to say how this function computes. We're viewing it as an eliminator for the natural numbers. So we started off with the rule version of the elimination and said if we have a term that's a natural number, this is what we can do with it in this rule form. Here we've basically got the three premises we had for that rule at the start. We had first we need to establish that we've got a predicate, which we've now replaced with a type family. Then we need an element. Then we need a proof of P0, which we've now replaced with an element of the type P0. And then we needed a proof that for all x, if P holds for x, P holds for the successor of x, which we replaced with a function, which is an element of this type. And then our eliminator said, then using that information, we apply that to the term T that we have of natural numbers type, and we get that P holds for the natural numbers T. So now we want to get that by applying this function here to the term t natural numbers type. And to see what, and here, this is a function that for every natural number will give us an element of p of x. So to see how this function works, we're going to look at what it does on x is equals 0 and how it behaves then for every successive natural number. And these are the computation rules. So when we apply p df, this function, to 0, well, what we want to get is an element of the type p0, and we have such an element b, so we just return that. So this is a computation rule, so this, and when we have this information, this computes to p. And when we want to compute recursor on successor natural number, n is a term here. Well, it's called a recursor because we're going to do it by recursion. We're going to recursively compute p, the recursor on p, b, f, and n. So if we recursively compute the recursor for natural numbers on the same p, b, on the same data, but for the number n, well, this gives us an element of the type p of n. And with an element of type p of n, we can apply the function f to it to get an element of the type p of successor of n, which is what we need. We want to get here an element. This needs to be an element of the type p of successor of n. So this is here is an element of p0. This is an element p of successor of n. Well, it's not yet, but we want to. So we want to apply f to this. And f actually takes two arguments: first a natural number, and then an element of type p of x. So we need to also give the number n here. That's an argument. Okay, so this is how it computes. And for people who've done the concept of primitive recursion before, this is basically computation by primitive recursion. You haven't, then never mind. But I'm going to give you an example. The point of this actually gives us a powerful method of computing with natural numbers. I'm going to give you a very simple example of its application, which is pretty much, you'll always see this as the first example because it's the natural first example. Maybe it's a good idea to keep this just to begin with, just the time here, and then I'll rub it up. So this was, here we had I at type. The example we're going to give is how to use this. At the moment, as a basic information with the type, all we've got is 0 in the successor function. So let's see how we can compute more interesting functions on the natural numbers. And the basic starting point one always begins with is addition on the natural numbers. So let's do addition, and then I'll let you do some other examples yourselves, maybe in the exercise class. So addition, we want to define a function add, which is going to curry it. So we're going to give the arguments one at a time. but it's a two-argument function. We want to give it m and n, and we want it to be the sum of m and n. Okay, so add, I want to define it using the recursor. There's going to be a function from natural numbers to natural numbers. Sorry, from current two arguments of natural numbers to the natural numbers. So we can always begin it with two lambda abstractions giving us the two arguments. So we'll have the first argument, the second argument, and now we need to give something that says how we add m and n together. The point is to use the recursor, and for the recursor, we need to give a family of types, and we need to give a starting value, and a way of iterating it in such a way that it's going to work out the addition. So let me just write down the answer. And then I'll explain it. So family of types is just always for any natural number. So this underscore says we've got a variable, but we don't care what it's called because we're not using it. So for here, for every natural number, we're working with the type of natural numbers. And what we want to do is we want to compute the function m plus n. And so we're going to recurse on n. And if n is 0, we return m. And if n is not 0, then what we want to do is take whatever. So if n is not 0, so n is the successor of n prime. If n is the successor of n prime, then it's enough to compute m plus n prime and take the successor of that. And this is what this function says, give me the recursive value of the addition function on n prime, and I want to return the successor of it. And this first argument here is not needed because it's just we don't need an index for the well, that's because we're working with the same, with p of x is always an at, so it doesn't really matter what the x is here. So here it's just lambda of anything. Okay. So it's hard to give more explanation in the lecture than that. But what we're going to do is do a computation to see how beautifully type theory computes with these recursively defined functions. If you don't think it's beautiful, well, work some examples out for yourself, but just think that it's a miracle that we have this sort of very coherent framework with these nice, elegant rules for different types, and one can, with these rules, just define simple programs that begin to compute. We're building up additions. The first example of a function we compute, we're building it up in a sort of very methodical way from basic principles about introduction and elimination rules and computation rules. So another point of reference here is, as you may know, that logic basically in mathematics was a subject that started at the end of the 19th century. Logic was always there in philosophy, but logic as a formal mathematical subject started at the end of the 19th century, and there were issues in the way people were formalizing mathematics to begin with. So Gottlob Frege, the German philosopher, had a very famous approach to formalizing mathematics in logical terms that Bertrand Russell found a problem with, called Russell's paradox. And because of that, Russell, together with Whitehead, his collaborator, wanted to put mathematics on a more precise footing, and they developed the earliest version of type theory in their book Principia Mathematica. And their version of type theory was type theory from more than 100 years ago, so a lot of the insights that people have used since then weren't available, but they had a system, and it kind of worked, and they could derive some mathematics, and very famously, it's a very complicated and it's not really the kind of book you can actually open and read as a human being. There's lots of notation there, and very famously, somewhere deep into the book, after several hundred pages, I don't remember exactly, maybe there's even more than one volume, and it's in the second volume or something like that. Eventually, they get to the proof that 1 + 1 = 2. This is like a famous theorem of Principia Mathematica, and it takes a whole load of work to get there. So what we're going to compute, we're going to see how much easier 1 + 1 = 2 is in dependence type theory. We've got it. So we've got a plus now. What we're going to compute is that add of sub of 0, that's 1, sub of 0 computes to 2, which is sub of 0. Okay, successor of 0. Okay, so add. So add is this complicated term here. We're applying it to 2 arguments. So I could write out this whole term and then followed by these 2 arguments, which is the application. But basically, you're applying it to these 2 arguments. So with one, what's called beta reduction, which is the elimination rule for the lambda abstraction, we plug in this argument for n. And with another one, we plug in this argument for n. So in a sequence of 2 reduction rules, one for each of those plugging in. So here I write arrows star to mean I've used more than one rule. In this case, I've used 2. We get this term with suc of 0 substituted for n and successor of 0 substituted for n. So we get R nat. So instead of n, we have successor of 0. Get this function with a dummy variable. It's basically saying take the recursively defined value and take its successor. And n is again the successor 0. Okay, so which rule applies now? Which computation rule? The lower one. Yeah. So here we have the recursor with its type family, its initial value, and its recursive step applied to an argument which is a successor. So we're in this bottom rule, what to do if we get recursor applied to an argument which is a successor. Well, then we write out f, we write n, and we do the, and here we have, again, the recursor applied to everything, but now we go down to what was underneath the successor here. So this, in one step, goes to f, which is this. Sorry, it's this. I don't know if I pointed to the right thing. Applied to n, which is being under the successor here, which is 0. Applied to all this, but with just 0 instead of successor of 0, because take the predecessor of this. So this is that of feel like I should be giving some commentary, but I don't really know what to say. We're doing mechanical computation extremely slowly. But this applies to 0. Okay, so now we've got another function given by lambda abstractions applied to 2 arguments. The first argument is just forgotten because we didn't use it, so 0 goes away. So we plug that into this variable, which we don't need. And the second variable is associated to this. So we get back the successor of what we substitute for the second variable, which is all that. So 2 more steps, one for this lambda abstraction, one for this. So this is again an arrow star. We're using more than one step. We get successor of this. Nat of lambda. Type family, successor of 0. Okay. So what's the next step?
Yeah, fine, of course.
Yeah, very good. So now we've got a recursion given with three arguments followed by 0. So we apply the first rule, and it says return the second argument of the recursion. So for the not the p but the b, return the second argument. The second argument is successor of 0. So this goes to one successor here. Sorry, it's one step. One successor for this, and then the second argument here, successor of 0. And there we are. 1 plus 1 equals 2. Russell and Whitehead would be very pleased. Okay, are there any questions on that? Obviously, it's a little bit painful to do by hand, especially if things get 1 plus 1 equals 2, but if you try to do something a bit larger. But the sort of exercises to do now are to define multiplication, to try and define things like subtraction, which is a bit tricky because also you have to be careful. You can only you have to do truncated subtraction if the second number is bigger than the first. Anyway, you can play around, and maybe we'll do some playing around in the exercise class. I don't know. Okay, so that is the natural numbers. It's elimination rules and it's computation rules. Any questions on the natural numbers? Right, so now we need to do the same thing for lists and for vectors. Maybe I'll just do vectors. The lists are in the notes. I mean, the vectors are just like a more complicated version of lists where we take account of the length of the list. Okay, so our vector type is of the form vectors whose values are of type A, whose length is a natural number n. That's you. So it's going to be like lists. We have an empty list constant. There's a mistake in the notes here, but so the empty list constant we have for any type A, and its length is 0. And we have a cons constant, and the cons constant says for any length, so take a length, take an element A that we're going to cons onto the end of the vector, take a vector of A's of length n, and give me back what's the return type of cons? Anyone remember? Yeah, we're adding an element to a length of to the given an element type we're consing on, we're given a vector of length n, and what do we get back when we cons the element on? A vector of length successful. Okay, and to have it as a constant, we're using the dependent product here. And now, again, we have exactly the same situation as before. Our recursor essentially codes up an induction principle for vectors. We could have the recursor with as an induction principle about propositions, but in type theory we exploit the better generality to allow ourselves to inductively define families of types instead. So our recursion of vectors, I'm going to write it down in type theory, but I'll explain it in terms of the induction principle. So firstly, we work with any appropriate type family, which now we want to be a type family of vectors. So indexed by vectors. So to get type family indexed by vectors, we need to take a natural number, and then for any vector length n, that bracket's missing from the notes. I mean, it's implicit, but just to be clearer, should be there. Okay, so for all lengths and all vectors of length of that length, we have an associated type. But just think of this as a property of vectors. Okay, so for every length, but for every vector of every length, we have an associated property. Okay, so for all properties, if you like, then if the property holds for the nil vector, so for the property to hold for the nil vector, we need to also give the property the natural number argument, because the property is an element of a dependent product type. So we give it the natural number argument. So if it holds for the empty vector, and the next thing is going to be like the step case in the principle of induction. We now want to say if for every length n, it holds that when the property holds for a vector of length n, it holds for every const vector of length n plus 1. If that holds uniformly across all vectors and all vector lengths, then the property is going to hold for all vectors. That's what we want to say. So because of the lengths, it gets a little bit complicated to put that into type theory, but essentially just need to be careful what you write. So putting pi's in, but I'm going to read it as for alls. So for all elements that we might cons onto the list, and all lengths of lists that we might cons onto, and for all vectors of that length n, we want the induction hypothesis that if P holds for n, But if P for vectors of length n holds for the list A's of vector, the vector A's we've got, which is the vector of length n, then we want the inductive step to hold that P will hold also for the vector we get by consing A onto A's, and the cons also needs the length as an argument to say what's going on, and the P also needs the length of an argument, which in this case is P we're producing is of the length n plus 1. So we need P with the successor of n. But anyway, all this is saying, again, is for all elements we might cons onto a list, and for all lengths and all vectors of that length, if the property holds for the vector of that length, then it's required to hold for every extended version of that we've got for the version we've got by consing the element A onto the vector of that length. Cool. And so base case, step case, then hocus pocus, induction says, then for all lengths and for all vectors of the length, P holds for the vector, which has length A. Okay. Right, good. So that is formulated for type families, which is giving us a recursion principle rather than an induction, rather than only an induction principle. That I was explaining it in terms of induction. Anyway, it's a lot of symbols, but the intuition is, I think, straightforward.
Is it right to assume that this recursion constant is formed to the context that contains A? This type.
Yes, A should be a type here, yes. And so I'm doing the recursion principle for this particular vector type, for where A is a fixed type. I mean, so an even more general version would be to have vector as a constant where it takes as a dependent type depending on an A in type, but let's not go down that route. This is already general enough. So let's just do the recursion rules. So the computation rules in this case. So now, in order to do the computation rules, the general form of a recursor is its arguments, we'll give it a P, a type family that has that. So it takes vectors of length n types. So this next argument is some, let's see what I'm calling it, I'm still calling it B. So B of P of 0 nil. And this next argument has this complicated type. I don't really want to write that type again, so let's give it an orange box or something. So F has the orange box type, which is this. And then in that case, the recursion for vectors length the recursion for vectors applied to P, B, and F, then it has this type here for all natural numbers, for all vectors of length n, P holds for that vector. And all natural numbers for all vectors of length n. P holds for that vector A's. And we need to write the computation rules. Again, the computation rules are going to say what this does on the empty vector and what it does on a non-empty vector. So the first one for the empty vector is that the vector recursion will give a PBF. And for the empty vector, what other arguments do we need to give? So this is of this type. To give it the empty vector, we need to give it 0 for the length, together with nil, which is the empty vector. So the base case for the recursion is that. And in this case, what's it going to compute to? We want to get something of P0 nil. P, yeah, very good. And the vector P, and F applied to the successor of N and some cons A, and the vector we've got by consing the element A, oops, should be, we need to give cons its length, and A's. This computes to, so again, we do the recursive thing, and we do the vector recursion. Oh, let's going to need that. Well, let me just write it from. So again, we apply F. The point is to apply F to the recursion data. So we apply F to A, which we have, to N, and to A's, and to A's, and then we need something of this type, and that's given by the recursion. So now we apply the recursion vector to P, F, and A's. That indeed gives us something that indeed gives us an element of type P of successor. It gives us indeed an element of the type family indexed by successor of N and cons A of A's. Goodness me. So it's actually beautiful type theory for formalizing mathematics when you're writing down and the computer's helping you. Maybe this is about the limit or even beyond of what one wants to do on the board and actually write out by hand. So I think that's enough about these kind of types and their introduction and eliminator rules. That's to say, these are special, all these types are special cases of what's called an inductive type. And what are called inductive types. So NAT, lists, vectors are all examples of inductive types. And in fact, instead of doing them on a case-by-case basis, we could have done a systematic look at inductive types, and we have one way, one principle for describing how an inductive type forms its elements, and then from that you automatically get the introduction rules, the elimination rules, and meaning the recursive constant and the computation rules. But I think it's easier to understand with examples, and as I say, this notationally, it's already at the limit of what one would like to do on the whiteboard. Okay, so it's 5:02 now. We'll start again at 10 past. After the break, I still have 2 more slides to cover on type theory, but they're not things I want to dwell on. And we will have time to do that, and also then the discussion about the presentations. Anyway, we'll have a 15-minute break till 10 past. Okay, so I want to do two last things in type theory. So the first one is to enrich the logical language, so that at the moment we're able to encode the logical connectives and quantifiers in type theoretic terms by the way we encoded the propositions in types. We can't actually say very much of interest about the natural numbers. So, for example, we might want to prove, to state some property like there are infinitely many prime numbers or something like that. And in order to formulate that property, we would need to have a way of talking about equality between natural numbers. And we don't have, in the logic at the moment, we don't have any way of saying two things are equal. And one of the really nice contributions of Martin Luff when he designed his type theory was to realize that type theory has a very natural way of saying that two elements of a type are equal. And we want to have some sort of proposition that says we got two elements of the same type. We want to have the proposition that says that those two elements are equal. That may be a true proposition or a false proposition. Or thinking more constructively about it, we think about whether it's a provable proposition or not. But we still want to have that as a proposition. So what we're going to do is we're going to add something called propositional equality. And in fact, this propositional equality is another example of an inductive type. So if I'd given you like the general formulation of inductive types, propositional equality would be just an instance of an inductive type, but we'll understand it on its own. So we want to have an introduction rule, an elimination rule, a formation rule for when we can form the type, introduction rule, elimination rule, and computation rule. So formation rule is, well, to say what we want is a proposition that says that S and T are equal terms of type A. So in order for that to make sense, A needs to be a type. We need to be able to prove that S has type A. We need to prove that T has type A. And then we've got a proposition in that under those conditions, it makes sense to have a proposition that says that the two things are equal. Okay? The introduction rule. So we want to have a basic proof. We want a basic way of proving that two things are equal. Well, the basic way of proving something's equal is just, the basic rule is just that everything's equal to itself. So if T is a term of type A, then we have canonical proof that T is equal to itself. Such a proof is a proposition, hence it's a type. So this is, we call this REFL of T. The reflexive property of the term T, that's just a name. So the introduction rule come with constants. They come as named constants, just like 0 was a name for an element of the natural numbers. REFL T is a name for an element of this proposition type. It says that T is equal to P. And now, because it's an inductive type, the introduction rule and the formation rule actually determine the elimination, which is a recursor, again, like we had before. And I'm going to just write this down and say the briefest thing about an eliminator, about how to understand it. And then one other thing. Well, this is called very famous. Called J, in this case for type A. And in this case, it's going to, like we had the eliminators working for arbitrary type families P before, it's going to work for an arbitrary type family C.
where this is a type family over equality types. So we need to have an X in A and a Y in A. And then it's indexed by equality type, so it will map. So it's a family.
So this is J.
Sorry,
This is not a letter, not a town. J.
this is a J, J and Y, type A. So given such a thing, given such a type family of this type, C, then as long as the induction hypothesis holds, which in this case is this type family contains the diagonal. So it's inhabited for every diagonal element, x equals x. So for all x in A, if C holds the x and the same x again, where as the proof of equality we become reflexive, let's put an A tag on there as we will notice. So this is REFL AT. Then for all x in A and all y in A, we haven't proved that x equals y. What?
Excuse me, shouldn't this be refer AX, not T?
It should. Thank you. Well spotted. Then C X Y T. So really we view C as a property, as a predicate that contains variables X and Y. And C is true whenever the variables X and Y are the same. And this is saying then it's true, so whenever they're identical. And this is saying, well, then C is true whenever X and Y are equal elements. That's kind of how to understand it. It's not easy to digest this at first reading or even on many readings. As an exercise, which may be done in the exercise class, it's nice to use this to try and prove that equality is an equivalence relation. So it's reflexive and transitive. So to formulate that and to prove it. I don't want to say, oh, yeah, we do need to say something about the computation rule. So the computation rule is, again, what happens if we apply an eliminator to something that's got by an introduction. All the computation rules for the natural numbers and lists were like that. We said how to recurse on 0, one of the introduction forms, and on a successor, or on nil and on the cons. So here we need to say how we apply the eliminator to a reflexive element. And so the computation is this, that if you give J, A, C, F, T, T, and the reflexive constant for A and T, then you get back T. You can think about that in your own time, because I don't want to. So I just want to raise that there is this important rule, and you will appreciate it more when you prove that equality is an equivalence relation. The other point I want to mention about this is that this is not the form that Martin Lough introduced the rule. So here, equality is a proposition, which makes sense if we're thinking logically. But Martin Lough was working in his propositions as types interpretation. He didn't have a specific notion of proposition. Propositions were just simply types. So for him, the Martin Lough's version is that equality is a type rather than a proposition. So this is called equality types. Everything else is the same. And equality types
the idea is that now saying inequality is a type, so there may be different interesting ways of saying two things are equal. And in the noughties, it was discovered that these rules exactly correspond to rules that one might have for understanding this equality as homotopy. It has been as there's an interpretation given of type theory of types of topological spaces, and this equality relation was that the S and T are homotopic in these spaces. And this is the whole, so this having equality of types is the whole basis. So this is important for the equality types for what's called homotopy type theory. It's crucial for homotopy type theory and univalent foundations. There's a famous axiom called the axiom of univalence, which relies on having equality types, not propositions. Univalent axioms. And, these are like much more advanced topics, which we won't go into. So that's one thing. The last thing in type theory is to give you the rule that was missing from that formulation. And this is to do with this issue that arises in type theory, that suppose we've got a proof that U is a term in type B, where B had some variable X, and we've substituted some term S for it. And suppose we've got another term T that's basically equal to S in a very strong sense. For example, maybe it computes to S. So here we might have S might be 2, canonical form successor of 0. And T might be that complicated form we had it for it as, well, it's not that complicated, but it might be add 1, 1. So they're two different terms. Can we get that if T is that term, we expect to be able to derive also that U is an element of this term. And we can't do that in type theory with the rules we've got. We need a special rule for this. And for this, we need to have a new judgment form to say that if U and T are equal in a very strong sense, judgmental equal, then the type A, then we have this rule. So this is called the substitution rule. And for this, we need a new judgment. U and T are terms of type A that are judgmentally equal. Meaning, sorry? Oh, yeah. Because in my notes it's U, but on the board it should be S. Yes, thank you very much. S and T. And basically, this being judgmentally equal just says they both compute to the same thing. That's one way of defining it. Okay. So the rule for judgmental equality is that if S and T are both terms of type A, if S computes in many steps to here we're having a U to U, and T computes in many steps to the same term, then S and T are judgmentally equality. So are judgmentally equal. It's a strong form of equality because you can only prove it using this rule. So it really means they compute to the same thing, essentially. It's a bit more subtle than that, but that's a good intuition for it. Whereas the propositional equality is like a logical equality that we can do logical proofs and make assumptions about it. So the logical equality is itself a type. Or rather a proposition in the form we're having it as propositional equality. Whereas this is not a type. We can't reason about this. It just gives us a way of saying we can see these two terms of computation equal, so where we can use one term, we could also become the other term. And with that, that completes the presentation of type theory insofar as I want to present it. There are a few, I've not been as formal as possible. There's the issue about that I didn't use the type universes that Gregor raised earlier. But apart from that, I've tried to present it in what I think is a palatable way, because it's very, very formal stuff. It involves lots of notation. And then some ways when you start using the proof assistance, you get to appreciate the notation a bit more. So we need to wait for that to happen, and that's going to be happening in the rest of the course. So on the exercise class side. So before going to talking about the presentations, are there any questions on type theory? And after that, I'll stop the video. Okay, so I think that's all we're going to record for today.